not see it this morning?
But
we're not done
I'll check. Yeah.
But yeah,
it's that close.
It is that close, yeah. And along the way, there's this mind the gap performance improvement. So this is sort of a homage to when we were in London and constantly being told to mind the gap as you get off the trains. And on the read side, so when you're doing, we do aggregation of reads. And the idea is to say that if you have reading a region of disk and a reading another region that's right next to it, then we'll take those two, aggregate those into one read buffer, and do a single read I/O to the disk, because that makes it go faster. Well, something that comes up reasonably often is when you have these two regions, but they're not exactly adjacent. They're a little bit separated. So we put some code in a while ago that says, if you're doing a read and there's a little bit of a gap between the things you're reading, that's okay. Just aggregate across the pinky to pinky range here, read the whole wad, and this bit in the middle, the thumb to thumb part, well, we'll just throw that away because it's harmless to read it. Nobody cares about it for purposes of this. That's fine. Now, of course, in the case of writes, that's potentially more awkward because somebody says, I want to write this, I want to write this. There might actually be data there that somebody does care about. So you can't just blindly overwrite it. But what turns out is that because of the way RAID-Z works, there are sometimes these little gaps that we have to leave. Essentially, it's however many parity disks we have to round up to that, a multiple of that, so that in the event of worst case fragmentation, we can at least make gang blocks out of the storage. Sort of a long implementation sob story, but what it turns into is you can have adjacent regions of data with one blank sector between them. So what the right side mind the gap thing does is it says, in the case of these one sector gaps between writes, go ahead and create an optional I/O that spans the region between that would allow those to aggregate. And it turns out that that actually improves write throughput quite a lot for RAID-Z. If you look back to the 2008 Q4 release of the Amber Road projects, you can see that performance, as you went from, for a given number of disks, if you worked your way from mirroring through RAID-Z1, RAID-Z2, RAID-Z2 with wide stripes, and RAID-Z3 with wide stripes, that you got progressively less write throughput as you went. In the new code that Adam's going to be putting back shortly, mirroring is actually the lowest bandwidth option compared to any of the RAID configurations.
Yep, and that's just because the way allocation works and the fact that we round robin through these mirror things, we wind up just sending less I/O to each disk, and it winds up being a little less streaming in that regard. Whereas here with RAID-Z stuff, because it is a single stripe, what happens is we're able to just stream solid to each one of the drives and get it a lot closer to its full bandwidth potential.
And if you think about it, it should be the case, right, that in general, you actually ought to get more write bandwidth out of a RAID configuration, because when you're doing mirroring, you have to write each piece of data twice. When you're writing RAID with, say, a 4+1 configuration, you're only writing 20% or 25% extra in terms of parity.
Instead of 100%.
Instead of 100%. So right, what you'd expect really is that as you get to the slightly wider stripes, right, like the RAID-Z3 wide stripes, well, we went from RAID-Z2 to RAID-Z3, there's more parity information, so that's not a big surprise.
But it's still not 100% overhead.
Right, exactly.
All right, dedupe. Yes. So, deduplication, which I think in the material for this talk was probably the title of this talk. The idea there, as many of you are aware, is that if I have a storage pool and I'm writing a whole bunch of data there, wouldn't it be nice that if previously I had written some random block of data, say Hello Kitty, that then later, if I happen to write Hello Kitty again, because I've already got it on disk, wouldn't it be nice, instead of writing a second copy of Hello Kitty, if I could just add a reference on the copy that I know I already have? And that's exactly what deduplication does. The principles are fairly straightforward, which is I have some data structure in which I look up references of this block. And so we use the cryptographic half signature of every block to look up in this data structure. And what we do is we say, have we ever written a block with this half signature before? If the answer is yes, awesome. We just add a reference count to it, in that data structure, make note of that, and don't actually have to do the write. We just have added a reference count. On free, before what would happen is you never would have to update anything on disk except for the space map when you did a free. Now what you have to do is you have to go to this data structure you're having off to the side, decrement the reference count, and don't free anything until the reference count goes to 0. So that's the basic high-level principle of this. And where this comes up a lot is any place that you have tons of duplicated data. For example, in virtualization, where I have a bunch of, say, VMware disk images, this happens a lot because, say, like if you're doing Windows on these virtual machines, you know, 80% or 90% of what's on disk is just another copy of Windows. Why do I have to store, you know, n copies of Windows when really all I need is one copy? And backup servers is another one. If I keep sending incremental backups of the same data set over and over, I just really want to be able to read the data if it ever comes to that. I don't actually want n copies of the data just because I've, you know, done n backups.
But Bill, I don't really do virtualization much, and I don't really run backups. How does this help me?
Yeah, and of course, the way to get anything implemented is to let a developer scratch their own itch with it. And the particular itch that Jeff and I have is we have, you know, a lot of build environments. We have a lot of copies of Solaris, 98% of which are the same, and all the objects that get built are the same. Wouldn't it be nice if on our little storage pools that we create for building Solaris, if we could just have n workspaces and all the blocks that are the same, we just have one copy of that data. Much more mileage and much more, you could stretch your in-memory cache a lot further with this as well.
Right, because not only do you want to duplicate on disk, but if you just do it in a storage appliance and that's all, you really lost a lot of the potential value because DRAM is a much more precious resource than disk is. So if you reduce your data footprint 100 to 1 on disk, but it still inflates by a factor of 100 in DRAM, then you really haven't solved much. So if you think about running a virtualization form, you've got lots and lots of VM images running. You want to do exactly the same thing that the OS already does with, say, libc, when you have 1,000 processes running. You don't have 1,000 copies of libc in memory. You have one copy, and it's a shared page. So the same principle applies. We already have support for this. For example, you have a file system with multiple snapshots. There's only one copy of any given block in the ARC because it's an address-based cache. For the same reason, when stuff is deduped, there's only going to be one copy in the ARC. Big win on DRAM space.
Yep, and of course, it behaves just like you would expect anything from ZFS to behave. It's always transactionally safe. It plays well with other ZFS features. So one of the things you have to have in order to turn on deduplication is a cryptographic hash. You know, right now we have SHA-56. There will probably be other options coming in the future. But one thing you would want to say is say ZFS set dedupe equals on for a given file system, and have it upgrade your checksum function to something cryptographically safe, you know, if you need to, and just do all the grunt work that you would otherwise have to do automatically behind the scenes so you don't have to worry about it. Question?
How does it work with quotas? User quotas?
So the way it works with quotas, and this is obviously a very thorny problem, is it works kind of the way it has to work, which is every single person storing a block, whether it's deduplicated or not, gets charged for it. So if we deduplication is really a cool space-saving feature. It doesn't get you extra mileage on your quota like compression does. And the reason is because you wind up with what's called the last reference problem. Is imagine that, you know, you stored Hello Kitty, I stored Hello Kitty. Well, if you stored it first and you got charged, then I stored it and I didn't get charged. What happens when you remove your copy? Someone has to be charged, but we don't have that information. We have to have a reverse map of every single reference to every block, which is way too expensive to maintain. So instead, it's just the administrator gets the advantage, everyone else still gets charged for space. Yes?
It strikes me there's